Hello, everyone. Thank you for being here. My name is Timur Doumler, also known as Timur Audio on Twitter. I am developer advocate at JetBrains. We make developer tools, for example, the C-Line IDE and other stuff. This is actually talk 2 of my 3 talks in a row talk marathon here at this conference. So I think going well so far. And this one, I was actually not supposed to give this one. I only signed up for this one 2 days ago because they had some free slots available. This is a talk that I was originally preparing for another conference, which is going to happen later. So I only put together the slides this week. I haven't practiced this talk at all, so don't know how this is going to go. This is the kind of very spontaneous one, this one. So I would really appreciate, because of that, if you could give me feedback afterwards, because it might be quite a little bit raw around the edges, like if you find anything that's wrong that you don't like, where like the pacing of the talk doesn't quite work or whatever, like please let me know, because this is a talk that I actually supposed to prepare for another conference later, so I'm still working on it. So I would really appreciate your feedback on this talk. Anyway, this talk is about C++23, which is not yet the official standard, but it is now feature complete. This is something that happened just 1 month ago at our last committee plenary session. So it's not done yet. We have about half a year left to fix bugs, which is called ballot resolution on the committee. It's 2 more committee meetings, basically. I don't think anything dramatic is going to happen in these 2 meetings, so we basically know the feature set of C++23 already. So that's a great time to talk about it, even though it's only going to be officially become the standard next year. Developing C++23, I mean, I should say I'm a member of the committee. I've been on the committee for about 7 years now, I think, so not as long as some other people, but long enough to have been around for some of C++17, all of C++20, and now all of C++23. And 23 felt very different because it was all done remotely. Because of the pandemic, we had to do all the committee meetings online, which was a completely different way of working together. And we didn't have an in-person committee meeting since February 2020. And I think that's part of the reason why we didn't get all the things into C++23 that we wanted to get in. So we didn't get executors, we didn't get networking, we didn't get pattern matching, we didn't get contracts. But given the circumstances, I think the committee did a pretty good job, because we did actually get a lot of really good stuff in C++23. So there was a lot of good stuff in there, and as I was preparing this talk, I was like, okay, but which of these should I talk about? And I have done talks about C++20 like 3 years ago, when that was the thing that we were working on. There were 2 of them. One was a talk at CPPCon, C++20 The Small Things, which was like a talk where I talked about 30 different features that were in C++20. And I thought, yeah, I don't really want to do that kind of talk where I just talk about one feature after the other, because like there's not really enough time to talk in depth about any of them. And then the other talk that I gave on C++20 was called How C++20 Changes the Way You Write Code, and I shamelessly stole the title from that talk for this one, which is the 23 edition. And at the C++20 talk, I talked basically about the 4 big features of C++20, which were coroutines, concepts, ranges, and modules. And obviously those 4 change the way we write code in very, very significant ways. They're not just tools you can use. They change our mental model of what C++ is and how we use it, right? So they change the way we think about functions, the way we think about templates, the way we think about algorithms, and the way we think about, organizing and compiling and packaging our code, which are extremely fundamental things. So I spoke about those 4 in that talk. And C++23, by comparison, is a much smaller release, right? We don't have these features that are going to completely change the world like these. But I would argue that it still has a handful of features that will change the way people write code, and it will change the way people think about C++ and learn C++ and use C++. The way I think about this is that C++ is basically like a really large toolbox, right? So you have your saws, chisels, screwdrivers, and then you have some. If you talk about screwdrivers, for example, you have like slotted screwdrivers and Phillips screwdrivers and maybe Torx screwdrivers. And then, someone invents a pentalobe screw, which, it's great for a particular type of product. Maybe it solves a very particular problem. And hopefully, like, if you have that problem, you're going to reach for that pentalobe screwdriver because you need to fix your iPhone. So you're going to reach for that screwdriver, right? And most new features in the language are kind of like this, right? But what I want to talk about is not that. It's more like features that are like the introduction of the cordless electric screwdriver, right? Which is really going to change how you deal with screws in general, right? You don't have to turn the screws by hand anymore. You can just go bzzz, right? And that's a game changer. So these are kind of the features that I'm more interested in. Like everybody should be aware of those. And we have a few things in C++23 where you can argue, they're kind of like that. So what is in C++23 as of right now? Again, like there's going to be half a year of bug fixing, but there's not going to be any more new features added because we are past the feature freeze. If you go to CPP reference, there is this page there. It's called C++ compiler support, and it has this big table which basically enumerates all the features that are in the C++23 draft as of now. So there's a long list of core language features. I'm sure some of you have seen this table, and then there's an even longer list of library features and which compilers already support them, basically. So that's a very, very long list. That's a lot of stuff, actually, right? It's small release, but maybe not that small. We have so many features in there. If you zoom out, this is what it looks like. It's quite a long list. This leftmost column, these are the actual features. Almost half of these, by the way, got approved just at the last plenary meeting in July. So that's pretty interesting. Let me just extract this kind of leftmost column into one slide. And then we get basically 3 pages. It doesn't even fit into one page. So here's all the new core language stuff. And then we have 2 pages of new standard library stuff, right? That's all in C++23 now. And obviously, I don't want to talk about all of this. This is way too much. Like, I would spend a week talking about this. So I need to kind of whittle this down to like end up with like a few features that I think are most significant. So how am I going to do this? I looked at this and I went ahead and I removed all the defect reports, deprecations, undeprecations, clarifications. There's a lot of like make something const expr, make something no accept, add a new constructor here. So I just, said I'm not going to talk about any of this stuff. Then there is a big topic, character encoding and Unicode support and all that. And a lot of work has gone into that in C++23. Big shout out in particular to Corentin Jabot, who has done a lot of work on that. Unfortunately, I'm not the expert. I don't know how text works in C++, so I'm really not qualified to talk about that. If you want to know about that, talk to Corentin and the other people who have done work on this. And the same with ranges. There has been a lot of work on ranges. A lot of stuff got added to ranges compared to C++20. And again, it's quite a big and complicated feature, and there are brilliant people who are doing talks on ranges and the new stuff in C++23. So I'm just going to, even though it's very interesting, not talk about that. So there are talks about ranges, and there are brilliant people doing those talks. So go there if you want to learn about ranges and all the cool new stuff in ranges in C++23. Not going to talk about here. And then I went ahead and also kind of removed everything else that I felt was cool, but it was like an addition to an existing feature or an improvement of an existing feature rather than a completely new feature in its own right. And so if I remove all of these things, then everything kind of fits onto one page. And this is kind of the list of really brand new features in C++23 that are not improvements or additions, but just completely new stuff. And we can consider talking about all of this. Now, a lot of them are kind of relatively small and relatively self-contained and specialized. So these are kind of the pentalobe screwdrivers or something like this. So I don't want to really talk about those. So I remove all of these, and we're left with this short list, which is kind of the bigger features. This is kind of the meat, right, of C++23. And yeah, this is a good list. It's a little bit too much for 1 hour, so I need to whittle this down a little bit further. These two are kind of complementing C++20, right? So we now have the standard library as a module, and we have some rudimentary support for coroutines in the standard library in the form of the generator. It's not really something completely new. It's more like complementing C++20. And then we have these things: stack trace library, move only function, flat map, flat sub. Super cool, great additions to the standard library, very useful, and you will use them if you need them. But again, I would say they're kind of self-contained. They don't touch other stuff around them. They're like, this is this feature, it's great, you can use it. So they're great at their job, but they will not really change the way we think about C++. They will just kind of give you another tool. So I'm not going to talk about these, and then we're left with these 4. And that's what the rest of the talk is going to be about. And I believe these are kind of the cross-cutting C++23 features that every C++ developer should be aware of, and that will have the biggest impact on how we think about C++, how we write C++, how we learn C++. So let's talk about these 4 things. Let's start with deducing this. Deducing this is by far the most significant core language feature in C++23. So it's not like modules, which like changes the entire ecosystem. It's not like that. You can certainly write C++ without knowing about deducing this. But it's actually surprising how many consequences this feature actually has and how much benefit it gives you. So I think you should really be aware of this. This is the front page of the paper, the proposal. According to Ben Dean, who is one of the authors, this feature has been kind of gestating since somewhere around 2013. So the idea has been floating around for a while. It took a while to standardize it. We now have it in C++20. Ben Dean himself gave a fantastic talk last year at CPPCon called Deducing These Patterns. If you want to know all the details about this feature, I recommend you watch this talk. It's like a whole hour just about deducing this. As of right now, I think this is the ultimate reference on deducing this. Obviously, like, I'm not going to repeat all of this. I'm going to give a little bit of a condensed version. But yeah, deducing this is remarkable because I remember, I think it was Bjarne, I'm not sure. Somebody said, there is this quote, if you're adding stuff to the language, which of those additions are actually good new features? And this quote says that a core language proposal is good if the proposed feature solves 3 seemingly unrelated problems simultaneously. Right, then it's a good feature which is worth adding to the complexity of C++ because it gives us all this benefit. And it turns out that using this actually fits that pretty well. So here's the first problem that it solves. So let's say we have a template or just any class in C++, and as you probably all know, you can overload a member function on whether or not it's const. Basically, whether or not this object itself that you're calling it on, whether or not that's const. This is, I hope, well known, hopefully to everybody here. Somewhat less known is that you can also overload a member function on whether this object is an R value or an L value, and you do that by adding these ref specifiers here. And you can also combine this, and then you get these 4 overloads, ref, 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 and then const ref and const ref ref. And so that's something that comes up, and it's kind of the simplest way of thinking about using this is that the first thing it does it adds a new syntax to write the same thing, because it's like this kind of weird thing you have this like thing at the end, which is saying something about the implicit first argument of a member function, which is the this pointer, right? It's the implicit first argument that you don't write. So the first thing that deducing this does, it actually lets you write that explicitly. So now you can, it's just a different syntax for exactly the same thing. So you can now write this parameter declaration, and then that's the implicit first argument, which is now being made explicit, and you can spell out now whether that's const ref, 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 const ref, ref, and so on and so on. So that's just another way of spelling the same thing by making this first argument explicit rather than implicit. And the other thing that lets you do is it lets you name that, right? So I can just name that argument, call it self. That's, I guess the Python people are probably used to this. But now the really cool thing is you can not only write it like this, but you can actually template on this. So you can write it like that. And all of a sudden the duplication goes away. So you can template on the type of this, and you can also template on whether it's a reference or an R-value reference or const or non-const, and you're going to get template argument deduction, which is going to tell you what it is. And because it's just a template, you can also use the alternative syntax here. And yeah, when is this useful? So the first problem it solves is duplication. This actually comes up. Here's an example. If you're implementing std optional value, it just returns, the value of the optional. But you have to do this kind of stuff because the optional could be reference, R-value reference, const, non-const, and depending on that, you need to return a different type. So you end up repeating pretty much the same code 4 times, which is ugly, right? It's the same logic. Why do you have to write this 4 times? And it turns out in C++20 and before, there isn't really a good solution for this. So one thing you can do is you can just repeat the same code 4 times, or essentially the same code. Another thing you can do is you can use one of the overloads, which is going to have the implementation, and the other 3 are going to kind of refer to it. But then you have to do all these ugly casts because like the parameter types and the return times, they don't quite match. So that's also ugly. You can also factor it out into a private implementation function, and you have the other 4 members kind of refer to that. Which is also kind of ugly. But in C++23, we don't have to do any of this stuff because we can just template on the type of self, and then it's going to look like this. So now you only have to write it once. And that's going to do the right thing here. And again, I have this new syntax, this, self, and self. I can write something else there, but I just call it self. And you also have the short syntax for that. So now this whole code just boils down to these 4 lines of code, and it works for all of these cases, and you don't have to duplicate anything. So that's the first problem that it solves. That's pretty great. The second problem that it solves is it solves the problem of the curiously recurring template pattern being a bit of a pain in the neck. I don't know how your experience was, but I remember what my experience was with this. This is actually one way in which a new feature can change not only the way we use C++, but also the way we learn it. So I remember how I learned C++. This is a picture of me many years ago. I was actually at the time working at the Astrophysics Institute of Potsdam in Germany. I was not doing C++, I was doing Fortran and C. And I decided I want to leave academia and become a C++ developer because I have just kind of discovered C++. I thought, this is really cool. I want to, do that professionally. And I was preparing for my first job interview. So what was I doing? I read Scott Myers. That was one book I read. And the other one was this online book, C++ Idioms. And everybody said, oh, this is the stuff that you really need to know. Like, this is the stuff they're going to ask you at the interview. So there's stuff like the pimple idiom, the erase remove idiom, and CRTP. And you really got to know these things if you want to call yourself a C++ developer. The pimple idiom, I haven't really seen it around as much anymore. The erase remove idiom we got rid of in C++ 20. We now have std erase. You pass in a vector. You don't have to do this ever again. So we kind of we are simplifying these things. These things are ugly. They're hard to learn, right? And one by one, like, we are kind of getting rid of them. And now we're getting rid of CRTP, which I'm very happy about. What is CRTP? Just quick primer for people who might have maybe forgotten what this is. Here's how you do, like, this is the classical polymorphism, the classical kind of object-oriented, like, this is the same you do in Java or any other, like, object-oriented language. You have a base class animal, and then it has a virtual function speak, and then you have like a cat and a dog inherit from it, and a cat makes meow and the dog makes woof, right? Everybody knows this. You're gonna find this in every programming book. And you have a reference to an animal or a pointer to an animal, and it's gonna call the right thing. If you do this like this, you have runtime, a virtual function dispatch, right? So you're gonna pay a runtime cost for this. You're gonna have virtual function dispatch, pointer indirection, blah, 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 blah. In C++, a lot of the time you know at compile time what the most derived class is, so you can just not pay the cost for that and do compile time polymorphism, and that's where CRTP comes in. And now you have to do this weird thing where you have your base class, the animal, and you template it on the derived class, right? This is what CRTP does. So you template it on the class that it's later going to be deriving, that is going to be deriving from it later, right? And then the other thing you have to do is you have to do this weird static cast to derived in order to call any of the functions. So this is kind of our virtual function call, but like at compile time. And then if you are inheriting from it and you're implementing your cat or your dog, you have to do this other weird thing where you inherit from the base class, but then you have to pass yourself in as a template parameter of the base class, right? This is how CRTP works. Everybody has seen this before, right? Has anybody not seen this before? Okay, a few people, but most people seem to be familiar with it. This is how you do compile time polymorphism in C++ 20 and before. And it's just super awkward, right? It's just weird. Like, for years, I couldn't remember if the base was templated on the derived or the derived was just templated on the base, and it's just not intuitive at all. This is one of those things that makes C++ really hard to learn. Well, deducing this makes it easier, because instead of doing this static cast derived thing, we now can just write this auto self, right? So we can use deducing this here. And the important thing here is that deducing this is actually going to deduce the most statically known derived class. So the type of the self here is going to be cat or dog, or it's not going to be animal. It's going to be cat or dog or whatever you're deriving from, whatever your most derived class is that's known at compile time, right? So this is already better because you don't have to do the static cast to derived thing. You can just call it, right? Because it's deducing the derived type for you there. And you will also notice that we don't need any of the template stuff anymore, right? Deducing this will deduce derived using normal template argument deduction rules. So you don't need to template on derived anymore. It just all evaporates. And we're left with this. It's much simpler code. We don't need any curious recursion anymore. We don't need any templates anymore. We just literally write, hey, take the actual class of the thing that you know, like the most derived one that you know of at compile time, and just call that function. And that's it. It's very easy. It's very straightforward. It makes CRTP completely obsolete. You can have more fun with this. Like you can write a concept, and then you can kind of constrain the member function, this argument on that concept being met by the derived class, right? So and then if we derive from animal and we don't implement this, like we have a fish which can't speak, it's fine. We can create one of those, and then if we try to make a fish speak, we're going to get a compile error saying class fish does not satisfy constrained speaking, right? So what we can do with this is we can basically constrain a member function on the properties of the class itself that is a member function of, okay? And by the class that it's a member function of, I don't mean the base class animal, which is where it's written, but the actual derived type, the most derived type that's known at compile time. So this is really, really cool. This is something that we could not do before in C++. And it opens a lot more possibilities. And if you want to know more about this, watch Ben's talk, Ben Dean, great talk. And here's the third problem that it solves. It lets you write recursive lambdas in a really cool way. And that one actually, I decided to skip for now. You can stay in the room and listen to the next talk that I'm going to give just after this one. And then I'm going to talk in depth about lambdas. And I'm also going to cover this as well. So this is really cool. Stay in the room if you're interested in how to do this. Right. This is deducing this. Next one, state expected. State expected, again, is a proposal that has been in the works for quite a while. The first revision, this is the paper, three authors. The first revision of this paper is from 2016. But actually, the idea can be traced back to this talk by Andrei Alexandrescu, which is from 2012. So that's like 10 years ago. So all these features that I'm talking about today have been in development for a really, really long time. And now you finally get them in a standard. And this is a tool for error handling, right? And the reason why I think it's so important is that error handling is kind of one of those cross-cutting concerns, right? If you start a new project, you should figure out how to do error handling from the beginning. Otherwise, it will be very, very hard to get it right later. And there are many, many ways to do error handling. We actually had a talk earlier yesterday at this conference by Vitaly on this topic. There have been countless talks given already about error handling. I think this is one of the most popular topics usually at C++ conferences. So there's a million ways to do it. They all have different trade-offs. And state expected is actually a really cool tool to have in the arsenal. Here's another talk by Phil Nash from C++ Now 2018. This is a really cool talk, 1.5 hours. He looks at something like 10 different ways to do error handling. Or you can return an error from a function, and you give like a scorecard for every method, like based on overhead, safety, noise, code separation, reasonability, composability, how much information about the error you can propagate. It's really worth watching. I don't have time to dive quite as deep, so I'm just gonna kind of scratch the surface. Here's a very quick, kind of simple example. What you're doing here is you're writing a lexer for JavaScript, right? And we want to parse a number. We have some source code. We have a string view that's like the source code, and it contains a number literal, like, I don't know, 3.5 or whatever, as a string. And you want to parse this and make this into a double, because in JavaScript, all numbers are doubles. You don't really have integers, right? So we just want to implement this, basically. And we're not going to implement this from scratch. We're going to use this wonderful standard library function std, which parses a string and returns you a double. And if you haven't been aware of this wonderful function until now you are. And then, so it's just going to return us the double, basically. You give it a string, it returns a double. And then we do this, which basically takes the string view and advances the beginning of the string view to after that string. So you can keep parsing other tokens afterwards, right? So we kind of just advance the begin pointer of the string view, essentially. And then we return the double value that we have parsed. So this is the implementation on the left, and on the right is the call code, where we have some source code which is not a number, and we are trying to parse it as a number and print it. And what is this function going to return? Or what is it going to print? Or what's going to happen here? Okay, it's going to print 0. Ish. Why ish?
Because double is never accurate. You can always get a little.
Well, no, but in this case, the string is not actually a number, so we get an error inside strtod. And what the strtod does, if it can't pass the value, it just returns the value 0. So you get the value 0. So you can't distinguish whether it's actually the literal 0 or whether something went wrong. So you need error handling here. So what does strtod do? If it can't pass the number, it's gonna write the value of begin into end. So we need to check whether begin and end are equal, and if they are, then something went wrong, and we can report an error. And here I'm gonna just do this with exceptions because this is kind of the default that we're supposed to use, right? So let's see what that looks like if we use it with exceptions. And then there's another case that can go wrong if your number is like your string is too long and has too many digits. It doesn't fit into a double, right? You have like 10 to the power of 1000, something like this. It doesn't fit into a double, so you get an overflow error, and the strtod sets the red val to like this kind of special macro value, and so you have to catch that as well. So these are the two possible errors that we want to handle, and one thing we can do is we can throw in an exception, right? And on the call side, we then have to. So basically, on the call side, we can do multiple things, right? We can handle the exceptions right there. We can write a try catch block, right? So we have to catch the individual exceptions. There's really good stuff about exceptions, right? It's a separate communication channel. It's not like the return value. It's like it doesn't pollute the function signature or the function call. All the error handling code is separate from the kind of business logic. And the other thing is we don't even have to handle this here if you don't want to, right? If the exception, if you don't handle it here, the exception can be propagated up the stack and it can be handled somewhere outside. And that's a great option if it's a critical error, that happens very rarely. And it's like, if this happens, we need to stop everything and tell the user, party's over, please try something else, we're done here. So that's great. But in this case, it's probably not what you want to do because this is not a critical error. This is something that's going to happen quite often. And it's something that's easy to recover from. You just try and parse it as something else. So, we can handle it right here in a catch block. And there's good news and bad news. If you use exceptions here, the happy path basically on modern platforms has like 64-bit Intel and ARM Windows, like Linux. Pretty much has no overhead. The sad path typically has a significant overhead, right? Because if you end up in this catch block, then you do have runtime overhead because you need to do all this extra work with doing the stack unwinding and everything, which you don't need to do here, right? And also it has a non-deterministic execution time. You can't really use it in any kind of low latency, time critical environment. And also like this whole information about how to unwind the stack is going to increase your binary size as well. So those are some of the reasons why community surveys consistently show that about half of developers work on code bases that don't use exceptions at all, right? So what else can we do in standard C++? Well, we can return an error code, right? So now we just handle it by, checking the error code. And now it's good because we're forced to like deal with it right there where the function call is. That can be a good thing for these like very common kind of non-critical errors that you can like handle immediately. We got rid of all the performance overhead, so that's very efficient. That's great. The bad thing is that the signature of the function now looks like this, right? So the error handling now takes over the normal communication channel of the function call, which is the return value. Now that's just the error handling, and the actual return value needs to be done by like this in-out parameter. So it makes the code ugly, hard to read, hard to reason about. So since I think C++ 17, we have std optional, right? Std optional is pretty great for this kind of stuff. We got a reasonable function signature again. Code looks clean. Got to handle it right there. We kind of check whether the number is there or not, and if it is, we can use it. If not, we can do some error handling. However, we lost the possibility to figure out what error we got, right? Because optional is just we have a value or we don't have a value, right? We don't have any information about which of the errors actually occurred. There's no way to do this. And we probably do want to tell the user whether it's a bad character error or whether it's an overflow error. This is like important information. So std optional is great where like the value is either there or not there, and it's either obvious why not, or it's unimportant why not. Like think about, I don't know, user preferences, and they have some, I don't know, and then, you know, maybe it's not there because the user has not set that preference. They have never gone into the settings to like tick a box there, so that information is just not there. That's pretty obvious. But like if you have something like this, optional is not really a good mechanism for error handling, in my opinion. And that's where expected comes in. With expected, which we now have in C++23, the function looks like this. So it looks very, very similar to the optional, except that instead of set optional, which is a value or nothing, we have set expected, which is a value or an error, right? So you can use any type you like as the second parameter, the second template parameter. It doesn't have to be an exception. It can be just a string with a message or whatever. It's very generic. And it's pretty easy to use. Like if we are on the left-hand side and we use that expected, we have a conversion, an implicit conversion from the value type to expected. So we can just return our double and it's going to be converted to the accepted. It's like the optional, right? So there's no syntactic overhead whatsoever here for the happy path, which is good. There is syntactic overhead for the sad path. The conversion from error to expected needs to have an explicit kind of std unexpected kind of thingy. So the sad path is kind of visible syntactically. The other thing is that on the Corley side, std expected is kind of like optional in that sense. It has a conversion to bool, so you can check it like this. It also has a hasValue method, just like optional. If there's a value, you can dereference it. It's just like optional in that sense, or you can write .value, again, like optional. So it's very unsurprising if you're familiar with optional. However, it also has this .error function, which gives you the error. And it's important to note here that .error is has a narrow contract. So if there actually is no error and you call it, it's undefined behavior. So you can always have to check whether there's an error, which is what we're doing here. That's basically the minimum that you need to know to use expected. And you can kind of figure out the rest as you go. If you're familiar with variant and optional and those other things in the standard library, then the rest of the API of expected is not going to be surprising for you. I would argue it's quite easy to use. So it fulfills also real need, because I think every application framework that I've ever worked on had something similar to std expected somewhere there. But the standard version is just much more generic and it's much more thought through, than all of these homegrown solutions, because they have really thought about all the kind of corner cases and everything, and it's a correct specification and a very complete specification as well. And so because of this, I expect std expected to pop up quite a lot in new C++ projects, right? I think it's going to start to be used. People are going to start to use it quite a lot. And that's why I included it in this talk. Of course, it's not a silver bullet for all your error handling. There are cases where you might want to go for exceptions. If you look at other more modern programming languages like Rust or Zig, they have really cool kind of core language solutions for some of these things, which are better than this. Also easier to compose, which with this is not quite straightforward. We don't have the kind of monadic operations in the standard for this, so it's kind of not easy to compose. This stuff, you can do it in Rust or Zig or any of these languages, so maybe we will get there someday in C++. We still have this paper from Herb from 3 years ago where he proposed a core language mechanism for zero overhead deterministic exceptions, which is actually really cool and low overhead and easy to compose. I think nothing really much has happened with this proposal in the last few years. I don't know. It looks like it's probably dormant, so I don't know if you're ever going to get it. Maybe you're going to get something else. But for now, we have std expected, which I think is pretty cool. Right. Let's go to the next one. Std mdspan. This is really cool. Here's again the paper. This paper has a very long list of authors. It's been in development for something like 8 years, or maybe even more. The paper number is P0009, so 18th revision was the one that actually got into the standard. So it's been in development for a long time. It's an old paper. We finally voted it into C++23 last month. And if you're doing scientific computing or numerics or digital signal processing or graphics or anything else that crunches numbers, then this is a real game changer. And I want to rewind again to my days before I became a professional C++ programmer. I was in astrophysics, and we were doing these numerical simulations like this one. It kind of simulates the large-scale structure of the universe. So we're here interested in kind of scales of galaxies and beyond. And the way you do this is you do like a discrete 3D grid. Imagine something like voxels, like 3D pixels. So you sample everything like this. You model the universe as basically a 3D box with this grid with periodic boundary conditions, because it's infinite, but you can't have an infinite box. And then you kind of throw together equations for hydrodynamics, gravity, and then cosmic expansion, and you just evolve the system over time. And this is kind of what we were doing. And you look what happens, and you hope that it's going to be somewhat similar to the stuff that you see on the sky. And this is kind of the research I was doing at the time. And I was writing lots of Fortran. This was all done in Fortran. This is the first programming language that I learned. And if you want to do this stuff, or many, many other kind of scientific numeric domains, you end up writing a lot of multidimensional arrays. So for that kind of stuff, obviously you have lots of 3D arrays, you have lots of 4D arrays, because you have 3 dimensions of space, and then the 4th dimension is like the quantity you're looking at, like density, velocity, whatever. So you have lots of multidimensional arrays. It's just what you have to do if you're in any of these numerical domains. And you have statically allocated arrays, and you also have dynamically allocated arrays if they're like really big or whatever. And I was doing this in Fortran. In Fortran, it looks like this. If you want to just have a 3D array and you want to initialize it, this is the way it looks like in Fortran. You just declare the 3D array here with its dimensions, and then you kind of write a nested loop, and you can write some numbers into it. It's not important like what this exactly is, but in the end, the array is going to be initialized. So that's how it looks in Fortran. That's nice and easy. In Fortran, multidimensional arrays are actually a core language data type. It's not a library thing. It's like built into the language, which is really cool. You can multiply a 3D array with a number, and it's going to do like the element-wise multiplication. You can print the whole thing in one statement. Like in C++, we now got formatted output for ranges now in C++ 23. In Fortran, you could do this in the 60s, right? So Fortran is really cool. If you want an array that lives on a heap, because it's big, you can just call it, like declare it as allocatable, and then you can allocate it. You don't have to worry about cleaning it up. It's going to do it automatically if it goes out of scope. So it's really, really easy to work with this. This is how I learned programming basically in uni when I was studying physics. And then I did this for a while, and then there was another project that where I looked at the code, and it was in C instead of Fortran. So at some point I had to learn C, which was like the next thing. And in C, well, if you have a static array, it's still reasonable, right? You can declare a multidimensional array like this. But if you need a dynamic array on the heap, this is how my supervisor taught me how to do this. And this pattern was all over the code base. Like it was like there was 100 places where you would see essentially this. And it was also in 4D and sometimes even 6D. So you can imagine like what that would look like. So first of all, here you do the allocation, right? And then it's declared as like the first allocation. The whole thing is declared as a pointer to pointer to pointer, because you have a 3D array. And then you have to actually allocate every dimension separately. And then this is the loop where you actually initialize the values or do something with it. Again, not really important what that is, but this is how you access it, every element. And then in the end, you have to clean it up again and again per dimension, right? And if you forget to do that or you screw that up, then you get a memory leak or something worse. And it's a very sad world to live in. And much later, much later, I learned that this is actually not great. Your array, in general, if you do it like this, will not be contiguous in memory. That's not ideal. So a much better way of doing it in C is to do this, where you actually allocate a 1D array, right? You allocate it once. And then when you loop at it, you just pretend it was a 3D array by using like 3D indices. And then you have this kind of element access formula where from the 3 indices, you kind of figure out like what element in the 1D array it's actually mapping to. And if you get this formula right, we can like compute that offset and then, this is C. In C++, we can do it a little bit better. Like we are doing essentially the same thing, but you can wrap it into a class, right? So we can make the element type a template parameter. We can hide this formula behind like some kind of operator paren, which takes the indices, and then the formula is going to be in there. And and that returns a reference to the correct element. Who here has written something like this in C++? Okay, this is like half the room. I had to write this at least 4 times, I think. This is not really a lot of fun, and especially if you are starting to do kind of more interesting stuff like template it on the number of dimensions, right? So the number of dimensions becomes a template. So all the member functions now become variadic templates, and they take a pack of indices, and you have to get that right. It gets even more fun if you want it to be const expert, because you want to benefit from optimizations if you know the size at compile time, or maybe know the size of one dimension at compile time, but not the other. This is really, really, really hard to get right, okay? And this is where mdspan comes in, because they have basically solved all of these problems and in this space, and we can now just use it. Okay, so how does it work? Same thing, some data, doesn't really matter where it comes from, it's allocated somewhere. And now we can declare an mdspan, we pass it a pointer to the data, and we pass it the extents of every dimension. And note that we don't have to write any template arguments, because mdspan relies heavily on ctad, so it kind of just deduces the template arguments for us. And once we have our mdspan, we can access the elements like this. And now there's 2 things that are noteworthy about this. First is it's not owning the data, it's kind of just wrapping it, right? And the second is like span, but in multiple dimensions. And the second thing about this is that the way we access this here is with this square bracket operator, and now it can take multiple parameters. And this is like a new thing a new core language feature that we added into the core language in C++23 to enable this syntax, which I think is a very, very nice syntax. And because it's not owning the data, you can have multiple mdspans accessing the same data, right? So you can view the same block of memory as a 3D array. You can have another mdspan viewing the same block of memory as a 2D array. There's no problem. There is a member function called .rank, which returns you what the number of dimensions is. And it can handle both static and dynamic extents. And the way to do this is you have this helper class that extends, and then you can tell it, okay, my index type, not the element type, the index type can be int or size t or some other integer type. And then we have 1 dimension, size 4, statically known at compile time. The second dimension, size 4, and the third dimension is dynamic, right? For example. And then you create this extends object, and then you create a mdspan, pass in your data pointer, and pass in those extents, and it just works. And another way to write the same thing is you can do it directly, because the extents are actually the second template argument of mdspan are the extents. So you can either let ctad deduce it, but if you want to do something more interesting, you can specify this template argument explicitly. If all your extents are dynamic, you can write it like that. Basically, this is the same as span. Span also has this dynamic extent. So we just took the same thing for span, and we now use it in mdspan. But if all of them are dynamic, then there is this very handy type def, which is called std_extends. It just means 3 dimensions, all of them are dynamic extents. So that's very cool. And actually, here's the full declaration of mdspan. It has actually 4 template parameters. The first one is obviously the element type. The second one is the extents. We already talked about this. Let's briefly talk about the other 2. There's the layout policy. This is really, really cool. This is basically this is the mapping formula. How does your mapping formula work? How do your 3D indices, or whatever, how many dimensions you have, how do they map to the actual position in the block of memory that you're wrapping? And there's at least 2 common ways to do this. It's row major order, which is what C and C++ use, where like the last dimension is like the one that's contiguous. And there's the column major order, which is what Fortran and MATLAB use, which is basically the other way around. And for some reason, C++23 calls them std layout right and std layout left. I have no idea why they didn't just say row major, column major, but it is what it is. So layout right is kind of the C++ way, or the C way, and then you can also use layout left, which is the Fortran way, which is the other way around. And then you have to write the loop the other way around, right? So if you do layout right, then the innermost loop is the index at the end, and then layout left is the outermost index, is the one at the end, the last index, right? So, but it's really cool if you're interfacing with Fortran code, for example. You want to look at the same array from both programming languages. And this is pretty great. And turns out not only do you have std layout right and std layout left, you actually can implement your own and plug that in. For example, again, when I was working in astrophysics and we were doing these simulations, there was a use case where we needed a Hilbert curve mapping, which is another way of mapping a 1D index into multiple dimensions. So this is how it looks in 2D, this is how it looks in 3D. And you can just implement this mapping, which is a different mapping, as a layout object. And you just implement some API that C++ specifies and just plug that into mdspan as the third template parameter, and it just works. And I wish I had mdspan back then when we were using this astrophysics stuff, because it would have made my life so much easier. It would have saved so much time. Anyway, you can write these custom mappings. They don't even have to be continuous, or they don't have to even be unique. Like, you can have different indices mapping to the same point in memory. For example, you have a matrix, you know it's symmetric, so you know that the upper quadrant and the lower quadrant, like the, not quadrant, what are they called? The upper half and the lower half, that they're the same. So you don't have to store the lower half. And whenever you index into the lower half, it's just going to redirect you to the upper half. So you save almost half the memory, right? So you just implement that as a layout, plug that in, everything works. It's beautiful. And finally, the last template argument is an accessor policy, which is once you have your mapping, you know which memory you're looking at to get an element. How do you actually access that? And the default is, well, you just return a reference to it. But you can do some more interesting stuff. For example, you can, instead of returning a reference, you can return an atomic ref if you want to look at the element atomically, if you're doing it from multiple threads or whatever. So you can, again, implement your custom accessor, and that's going to define how you look at the elements. So, and you can do even more interesting stuff with that. So this is super powerful, super extendable, I would say relatively easy to use as well. It's really cool. If you want to know more about this, there is, again, a talk about this by Bryce Lelbach, which is 1.5 hours of just explaining how mdspan works. And yeah, I recommend you check that out if you want to know more. mdspan actually pops up in all kinds of domains. It's not just this kind of scientific numeric stuff. Like, for example, when I finally left academia and got a job as a C++ developer, I went into music software and audio processing software and stuff like this. And there we have an audio buffer, which is like audio data, multiple channels, left and right, or surround or whatever. And it turns out, so anybody who has seen like my audio talks, like knows that, there's a lot of that stuff as well. You have different layouts in audio. You have like interleaved, de-interleaved audio files, channel layouts, and it turns out this is all just really special cases of mdspan. You can handle all of this with mdspan and like custom layouts and all of that. So this is super cool. So mdspan, as I said, it's non-owning, like stdspan. There's also std-md-array, which is like the multi-dimensional version of std-vector, essentially, which is not in C++23, but it's coming up, hopefully, in C++26. It's like the owning version that's going to actually deallocate the memory if it goes out of scope. So that's mdspan. That's really cool. And now we come to the last section of this talk, which is also very fun. Std_print, and this is literally changing the world, and namely it changes how you write hello world, which is something that hasn't happened in, I think, 3 decades. It's this paper by Viktor Zverevich, formatted output. Again, has been through a lot of revisions, this paper. And that is really cool. That solves a very interesting problem, which is how do you write hello world? So if you look at any programming book about C++, this is pretty much the first thing that you're going to see. This is from Bjarne's book, but you can open any other C++ book. This is the first code snippet in that book, which is literally hello world. You can also open any IDE and say, create a new project. I can do this in C-line, which is obviously my favorite IDE. And I can just go to a new project, and it's going to create a project which looks like this. Again, hello world. C-line and Bjarne don't agree on like some of the details. For example, C-line is using std_endl, Bjarne uses \n, and also C-line, the default template is going to return 0, which you don't really have to write. But that's not really important. Like, the important thing is the std_cout there. And let's ignore like those other issues for a bit and talk about std_cout. And so this is, again, Bjarne's version. So let's do a code review here. What's wrong with this code? What are the problems in this code? Hmm?
Doesn't flush.
Doesn't flush. Okay, yeah. That's one problem. More basic problem is performance. This is not good performance. Printf is a lot faster than this. Of course, printf is also not type safe, so it uses these like runtime periodic arguments. So if you use printf format strings, it's very easy to make your code crash or perhaps introduce a security vulnerability. And I think Patricia has a talk about that. That's a different topic again. But the fact is, even if you, even if you forget about that problem, std_cout is not that, like IO streams do not have great performance. They are really slow. Second problem is that the interface is really awkward. You have these like shift operators, and then you got this zoo of like so-called IO manipulators that you also have to pipe into with this shift operator. For example, you want to print a bool. What is this going to print? 1. Okay, this prints 1. What if you actually want to print true or false? How you do that? What? Yeah. So it's called std bool alpha. That's the thing you need to put in there in order to print true or false. And there's a whole zoo of these manipulators. Some of them are included in header IO stream. Others, like setw, which is the one you need to set the field with. You need to actually hash include IO manip to get that. It's very difficult to use, very awkward interface, but that's not even the worst part. The worst part is this is like the English version. And if I write this, then it's going to print hello world. But if I want to do the same thing in my mother tongue, I write hello world in my first language, which is Russian, Привет мир. And I get this, at least on Windows, which is not what I wrote there. It's very sad. I don't fully understand why this is the case. Maybe Victor or Corentin and somebody else here can explain it to me. I know that it has something to do with code page 437 and how Windows handles encodings on the terminal. I don't really know what that means. Maybe you can explain it to me later. But the fact is, it just doesn't work. And this is one of those reasons why the Python people keep laughing at us, C++ people, because they have solved this problem 1.5 decades ago, right? This works in every modern programming language except in C++. So, we solved part of the problem actually in C++20. In C++20, we got std format, which is, another work by Viktor Zverevich, which is pretty great. So with std format, if you have Unicode non-English characters like Russian characters in this case, it kind of just works because it supports Unicode, and you also have the syntax to print variables, right? You have these like curly braces, which you can use as placeholders. So here we can print our bool there. First of all, it's going to do the right thing. It's going to print true or false. And but if you want to print it as an integer, like we can do that too. We put that in the curly braces there. It's safe. Like if we have that string is going to be parsed at compile time. If you have like if you forget to write the B there, we're going to get a compile error. Hey, you forgot to put an argument there. So it's actually safe. It doesn't care about locale, which is another pain in the neck if you're, working with IO streams. So we don't have to worry about that. Problem is, this is C++20, right? It creates the string, but it still doesn't print it. How do you print it? Well, you gotta do that again. And that's not great. So first of all, that's gonna allocate a temporary string object, which is potentially another memory allocation. We don't need that object. Second, it calls operator left shift again, which is a function call that we don't need. std_cout performs formatted output on a string that's already formatted. So that's also not just a waste of CPU cycles. And then it's still not going to correctly print my non-English Unicode characters because std_cout just doesn't understand Unicode. So even in C++20, this problem has still not been solved. But we now solved it in C++23 because now we can write this and everything is wonderful. You can write stdprint. Forget about std_cout. Yes, there's a question.
Yes, is there a way to make it really correct, which means not writing true in English, but writing true in the same language? In Russian.
Yes, the question was, what if you want to write true in a non-English language as well, and you can have a custom formatter for that and just kind of plug that in, right? Or use the local version. Does format work with locales? Yeah. Okay, I'm not...
You can actually select it as an option.
Okay.
And there's actually
actually been a paper about.
All right. That's super interesting. Let's talk about this later. I want to know more about this so I can include this in a future version of this talk because I don't quite know how this works. You were talking about locales over here, so let's talk about this later. Yes, there's another question. It looks very much like what? Yes, it looks like printf, but it's not like printf because it's safe.
Yeah,
right?
Except for not safety. My question is going to be: will this feature have all of the capabilities that printf has?
Yes, it has all the capabilities that printf has and more. The syntax is just slightly different. Like instead of, I don't know, %i, you need to write like :i, I think, inside the curly braces. So you have to learn a little bit of a new domain-specific language, but it's actually easy and it's very, very powerful. It's better than printf in every way, really. This is also very performant according to benchmarks. It's faster than std_cout. It has all the advantages of format, right? It supports everything that std format already supports since C++20. If you want to write to another stream than standard output, there's overloads for that as well. So this is just absolutely awesome. And yeah, so in C++23, we changed how to write hello world. The canonical way to write hello world is now this, except not quite. We actually changed hello world twice because now we also have standard library modules. So actually, instead of #include print, you can do import std. And that's now hello world in C++. So std print still doesn't print a new line at the end, which is why we still need that \n, but we have a thing for that as well. We now also have std print line, and that will print your new line at the end for you automatically as well. So I'm actually kind of curious which one of the two is going to establish itself as the canonical hello world. Is it going to be print with \n at the end, or is it going to be print line, which looks very much like, I think Java is print line, right? And lots of Pascal, so it looks a lot like, you know, other programming languages now. So yeah, very curious which one of the two is going to win. I don't know. Do you have any favorite? Who likes the first one more? Okay, 3 people. Who likes the second one more? Okay, cool. So then I declare the print line version as the canonical way to write hello world in C++ as of C++23. Thank you. And I think we even have 2.5 minutes for questions. Yes. Yes. The question was, if you have std expected and you use an actual exception type as the second template parameter, can you actually throw that? As far as I know, not by default. Like you would have to explicitly throw that somehow. I don't really know. I mean, if you want to use exceptions, then just use exceptions. So I don't think that makes sense, but I guess you can get it out with .error and then throw it. But you would kind of mix 2 different ways to do error handling. So I'm not sure when you would do it, but it's possible. It's not the default though. You can use exception. Yeah, Daniela is saying you can use exception pointer. All right, there's another question here. If you use std expected and you don't check whether the value is legal, exactly the same thing happens as with std optional, which is if you dereference it without checking it, it's undefined behavior. It's exactly like optional in that sense. You have the same interface. You have like operator star, operator arrow, you have .has value, and you have .value. I don't see any other questions, so thank you very much for coming. And if you want to stick around, we're going to talk about lambdas and recursive lambdas and all kinds of other fun lambda stuff. So hope to see you there. Thank you.